Hi, class. Welcome to the next section, chapter 12.5. Today we're going to talk about conic sections. I reminded you on the last video at the end, but I'll remind you again. If you are not familiar with conics and you feel like you need a little bit of a deeper dive into their structure and the way that they work, then please visit my pre-calculus material for the conic sections there. We go a little bit deeper than we do here. Um, and then same thing for the next section as well. So 12.5 conic sections. Let's go ahead and talk about what a conic section is. So a conic section is what happens when we intersect a three-dimensional cone and its inverted counterpart, okay, with a plane. So there's four types of conic sections. The first one is circles, parabolas, ellipses, and hyperbolas. Okay. So if I have a cone, okay, and its inverted counterpart, or maybe I'm thinking about this as the cone and this is the inverted part, it doesn't really matter. But if I take a plane and slice through this, um, every time I slice, all the different ways that I can slice through this hourglass, this cone, creates a conic section, right? This is a cone and the slices are sections of the conic, okay, if it makes sense. So if I go parallel with the base, then I'm going to get a circle. Okay, the intersection of those two items gives me a circle. If I come at a slant, okay, then what I'm going to get is a parabola. Okay, I'm going to get a parabola. So in this case, this is what my parabola would look like. If I sliced up here, we're in a different form, I'd have a different looking parabola. If I slice slanted this way, okay, so here I'm going through a side and the base. Here I'm slanted through both sides, through two sides, I should say, all sides. I'm going to get an ellipse. So that's kind of like a tilted circle, right? If I go parallel with the base, I'll get a perfect circle. If I tilt it, I'll be elongated in some form, and I'm going to get an ellipse. If for the hyperbola, it's similar to the parabola, except I'm not cutting through the base and the side. I'm cutting through both bases and the side. Okay, so like this, perpendicular to the base. And that will give me a hyperbola. Okay. So in this section, we will talk about parabolas, ellipses, and hyperbolas. Circles we leave out. You should, at this point, know the equation of a circle and how it's shifted. Again, I go over that in the review section for my calculus one and the trig part of my pre-calculus, right? So you should have learned circles when you did trigonometry at the minimum. So we're gonna kind of go through one at a time, but not circles. So we'll go through the parabolas, the ellipses, and then the hyperbolas, because circles are a very, very bland sort of conic. Um, it has a lot of interesting properties, which have pretty much been explored as much as we need to for this class already through your trigonometry. Okay, so parabolas. We're gonna look at this geometrically. We're gonna start with a graph, and then we'll kind of derive the things that we need to from there. Okay, so we're gonna start off with what's called a directrix. Okay, we have a directrix and an axis. This directrix is not an axis, but a lot of times we like to um, use the axis, the x-axis, as the directrix. Most of the time, however, or actually a little bit lower, to be honest with you, this is just a line. Okay, it is not the axis, it is a line that is arbitrary. Okay, it has a function and a meaning, but don't think of this as an axis. Okay, as the x-axis. This axis is not necessarily the y-axis either. It really depends on my parabola, right? Both of these axes, this directrix and the axis, is dependent on the formula that I have for my equations. Okay, so I have my parabola here. Okay, the lowest point or highest point, depending on the orientation, is the vertex, as we know. Then we have what's called the focus. Okay, the focus is inside of the concavity of the concave portion of my parabola, and has a special function for us. And then this is just a random point on my parabola. And this line represents the distance from a generic point on my parabola to the directrix. And this line connects a generic point on my parabola, literally anywhere, to the focus. And what the relationship that we have between the focus and the directrix is that the distance from any point to the directrix is the same distance as that point to the focus. Okay, so those two lines are always equal anywhere on my parabola. So that's why the focus is important. So in the pre-calculus course, we use this information to talk about satellite dishes, right? That's basically what a satellite dish does is any point that kind of hits the interior of the satellite gets focused towards a single point, which we call the focus. And so that is the relationship between any point and the focus and the directrix of a parabola. Okay? The axis is the line of symmetry for our parabola. It's the line where our parabola is symmetric, right? If we're to fold it across that, okay? The directrix is on the opposite side of the direction of concavity. So the focus is inside the concavity. The directrix is outside of the concavity, right? So it is not at the vertex. It is a distance away from the vertex. And the length from the directrix to the vertex, again, any point on my parabola, is the same as that distance from the vertex to the focus. So remember what I said, from any point, okay, any point on my parabola, the distance from that point to the directrix is the same as the distance from that point to the focus. So if I stay on my axis, the distance, this vertex is a point on my parabola, right? So the distance from the directrix to the vertex is the same as the distance from the vertex to the focus. Because again, the vertex is a special point on my parabola, but what I was talking about here is true for any point. So since this is true for any point, well, the vertex is a point, so this directrix to the vertex is the same distance as the vertex to the focus. Okay? So in fact, the length from the directrix to any point on the parabola is the same as the distance from that point to the focus. So I said it first, but in the writing, I said it last. So let's say that the directrix is located at the line y equals L. So in our case here, using this, it's a horizontal line, and I'm saying that it's at the location at y equals L. Okay. So again, we could say that that's um, y equals 0 equals L, right? So at the x-axis, but it doesn't necessarily have to be at the x-axis because our parabola can be shifted up and down, right, in any sort of form, or maybe my choice for the directrix is important to be at this value instead of anywhere else, okay? So for simplicity, we're going to say that the axis of symmetry, however, does lie on the y-axis at x equals 10. So say also that the distance from the directrix to the vertex is p. So if the distance from the directrix to the vertex is p, that means that the distance from the vertex to the focus is also p, since those um, two lengths are always equal. Okay? So then the distance from the vertex to the focus is also p. And so we can say that the vertex is at 0, right, on the y-axis, and then L plus p. So this should make sense. So again, if I go up L units, and then I draw a horizontal line, and then I go up p more units, and I get to the vertex, well, then that means that the vertex is at L plus p away from the origin, okay, in the y direction, up down direction. So we can say that it lies at 0, L plus p. Okay? And the focus is then at 0 and then L plus 2p, because remember, we go 1p up to the vertex and then one more of those distances to get to the focus. So say that we have any point on the parabola, and we'll call that point xy, we'll call it p, right? And it lies at xy, and somewhere on our parabola, anywhere. And so let's write all this down in a summary, right? So we have it in a paragraph, but I like to see things written down as a list. So my directrix is located, it is the line y equals L, so it's located L units up or down from the x-axis. The vertex is L and then plus P, right? I got to go a small distance up. And then my focus is two of those P's away from L. Okay, and I have a point XY. So far this is all I have. I also know that the distance from the directrix to the vertex is the same as the distance from the directrix to the focus. So I can start to do something with that, right? Specifically, in this case, from this point P, right? So from P to the directrix and P to the focus. Okay. So point P to the directrix and the point P to the focus have the same distance. Okay, so distance from P to the directrix. So here we're going to use the distance function. Okay, the distance function means that we subtract the x values, square it, add to that the difference in the y values squared, and then square root the whole thing. Okay, again, this comes from trig. You see this in trig a lot. It's you're just using a right triangle and you're looking at the hypotenuse of it, basically, right? And that's how distance is calculated. So I'm looking at the differences and the distances from P and L. Well, my directrix is a line, okay, at L. And so the distance then is just the horizontal distance, right? I drop a line straight down from P, okay, to get to L. I don't have to talk about how much over am I and how much up I am. I would do that when I have this point P in the focus. So from the directrix, I just need to drop down this much, okay? So this would be that little triangle that's there. Or all the way. And so from this point, I'm really just subtracting the y values, right? Okay. So x minus x, there's no movement in x at all, right? The x's stay the same. However, I have y from my point P, and the directrix is at y equals L. So I'm just subtracting those two and squaring it. So this is 0. Okay. I have y minus L squared, so then I'm going to take the square root of that. And so we're throwing this into absolute values because it needs to be positive, right? I can't have a negative inside of here because then I'd have an imaginary value, an imaginary distance. Doesn't make sense. So distance is always positive, right? Whether I walk 10 miles forward or 10 miles backwards, it doesn't matter because the distance I traveled is 10 miles. So distance does not have a direction, so make sure you're keeping this inside of the absolute value sign. Okay. So my distance from my point to L is really just that distance in y, right? The difference in distance between the y value here and the y value for L, right? So this y minus this y is that distance, okay? So that's basically what we wrote here. The distance from P to my focus, so we're going to use the standard distance function. So again, the distance from my point P to the focus is the difference in x values. Remember my focus, I'm saying lies on the line of symmetry, which we're calling the y-axis. So I have a value of 0 for the focus. So I have x minus 0, the difference in x values squared, so just x squared. And then the difference in y values, so y minus L plus 2p, y minus L plus 2p, and then squaring the whole thing. So subtract the x's, square them, subtract the y's, square them, add that together, take the square root. So y minus L plus 2p. Here, we've done this several times this semester, so you should be good at this. I square the first term, I multiply these two together and double it, and then I square the last term. Okay, so again, the distance from a point to the line L, the directrix, is the same as the distance from a point to the focus. Okay. So here I wrote in a small p, so please don't get that confused with this p. This should be the capital P for the point. In your course reader, I will make that adjustment, but I don't feel like doing it right now for the video, but that's all right. But we know these two values are equal. So this absolute value and this square root sign are both equal in value. So without actually expanding this, I would like to isolate this first. I will end up expanding this, but the distance between y and L is the same as the distance from the point to the focus. Okay. So now I want to start mathing it up and really just kind of see what happens. Ideally, when I have something equal like this, I have my y's and my x's, right? Those are my two variables, this L and this little p here. These are constant values, right? This is whatever the distance is from the directrix to that focus, right? This 2p. And so, yeah, so let's kind of go for it, right? Let's square both sides, okay? That gets rid of the square root sign, right? And then now I have y minus l squared. So I have this x squared and then y minus this value squared. So I really should probably just start to expand everything out and combine like terms, try to get things to cancel out, right? So y minus l squared, square the first term, multiply the two inner terms and double them. So minus 2yl, and then add the last term squared. Here I have x squared. Here, square the first term. Here, multiply these two together and double it. So negative 2yl plus 2p. And then square the last term. So I have l plus 2p squared. And the only reason I didn't pull this out is you can see I have another term here, but I'm not going to do anything with that because then I end up just refactoring to what I have. So the next step, let's go ahead and expand this right-hand side a little bit more. Okay, so remember this minus 2yl. Notice I have that on the other side also. And then this is, I got to expand this, right? L squared plus 4lp plus 4p squared. Okay, so the last three here is just me expanding this, right? Square this thing, multiply those and double it, and then square this thing. Okay, and then for this, I'm just going to distribute this across. So not too crazy. So the x squared and the y squared, and then here is me distributing that 2y across, and then this is me expanding that l plus p squared, okay, l plus 2p squared, I'm sorry. So now I just keep simplifying, right? I got a y squared here, I got a y squared here, they're both positive, so if I subtract one side from the other, they just disappear. So anytime I have the same thing on both sides, same sign and everything, they kind of just go away. So this y squared minus 2yl, y squared minus 2yl, that whole thing goes away. Here I have an l squared, here I have an L squared, so this gets to go away also, okay? And so then what I'm left with on this side is just the x squared, this minus 4yp, this 4lp, and this 4p squared. Okay? Um, see what I can do here. I can try to start to factor this again. If you notice there's a 4p in all of these terms, maybe I pull that out, maybe I don't. Okay? So here we're gonna get x squared on one side and everything on the other. Now let's go ahead and pull out the 4 and the p, and I have y minus l minus p. And then I want to get this in terms of something I recognize, so I'm going to pull out a negative, okay? And this is going to be, if I throw this in parentheses, it's 4p y minus l plus p. And this l plus p, if you notice, is how much I shifted the entire system up, okay, or down, right? Because I said my directrix starts at y equals l, and then I move up by P to get to my vertex. So this is actually the location of the vertex. So this is basically my upshift, right? 4P and then y minus however much I shifted up equals x squared. So note that 0, this L plus P, is the location of the vertex. So vertex, 0, L plus P. There we go. Okay. And so that's why I pulled out this negative sign so that now it matches something that I had already, which was the vertex. Okay. So this is where the vertex is um, when my axis of symmetry is at x equals 0 and my directrix is at L. Okay, so this is what the form of a parabola would look like. So x squared equals 4p times y minus l plus p. A lot of, so without this shift, if this shift was 0, okay, if I didn't move my parabola up and down at all, then this would just be x squared equals 4py. Okay, so uh, this is the equation of a parabola that has a vertex at 0, L plus p, with a directrix located at L. Okay, so we draw a nice graph. This is the directrix, y equals L. This is the distance between P and L. It's the absolute value of y minus L. It's just the difference in y values. The focus is at 0, L plus 2p, right? And the vertex is at L plus p. And that's because going from L to the vertex is the distance of p, and the distance from the vertex to the focus is the same as any distance from the directrix to the vertex. So if this is p, that means the focus is p away from the focus as well. So this is the graph that we get for a parabola that has its symmetry at x equals 0 and a directrix at y equals L. So let's say that our parabola has an axis of symmetry at y equals 0 instead. So instead of being opening up, it opens to the left or the right. Okay. Then our directrix wouldn't be at y equals something, it would be at x equals something. So we'll call that value L. Okay, so the parabola is rotated 90 degrees, either to the left or to the right. It doesn't really matter. We'll talk about how to tell the difference between if it's to the left or to the right. So the vertex will be located at L plus P, 0. Okay, so my directrix is at L. I move a distance of P, that's my vertex. If I move a distance of P more, L plus 2P, I'm now at my focus. Okay, is at X equals L. The vertex is at L plus P and 0. Focus is at L plus 2P and 0. Any point on the parabola is still XY. Okay, as long as it satisfies the function for the parabola. And then the distance between the point and the directrix is the distance between x minus L, absolute value. And the distance between the point and the focus is very, very similar, difference in x values. And then y minus 0, so that's just y squared. We do the same thing we did before, right? Do the math, set these two things equal, and simplify everything. And our equation will come down to y squared equals 4p x minus, and then my shift left to right where my vertex is at. Okay, so it's very, very similar. Instead of x squares is 4p y minus the shift, it is y squared is 4p times x minus the shift. Okay. So this is the vertex at L and P, and the directrix is at x equals L. So it will look like this. All right, this is the directrix. I move a distance of P, I get to my focus, I'm sorry, my vertex. I move another distance of P, so L plus 2P's. I'm at my focus. The distance from the focus to this point is the same as the distance from this point to the axis. Okay, I'm sorry, the directrix. So let's go ahead and do an example. Okay. So let's find the focus, the directrix, and the vertex for the parabola that has the equation 6x plus 5y squared equals 0. So first thing is we have to put this into the correct form. So remember the correct form, the square term is y. So this is the correct form. So I want y squared equals a bunch of stuff times x. If I can have it minus something, then that's nice. If it doesn't work that way, then that's fine also, right? And so that's how I want it. Some number times x, possibly something being subtracted, okay, or added. And so here, if I start to solve for y squared, so again, I'm just trying to get y squared alone. I'm going to subtract the 6x, okay, and then divide by 5. And so I have y squared equals negative 6, 5, x. Now that I have it in this form, I can, well, let's go to that formula. I'm not adding or subtracting anything, so I'm really just going to assume that the vertex is at 0, okay, since there's nothing being added or subtracted, so there's no sort of shift going on here. And so then that leaves me with 4p times x. So whatever I have times x then is 4p. Okay? So that means that 4p is the same as negative 6 over 5, which means I can start to solve for p. And once I have p, if we come back here, right, just giving us a direction, once I have p, I can figure out the vertex, I can figure out the focus, I can do all of those things, right? So I can find my L and all of those nice fancy things. There we go. There we go. Okay. So this tells me that L plus P is 0 because is very obvious. Nothing here is being added or subtracted to it. Okay, so then my vertex is at 0, 0. Okay. I know that 4p is the same as negative 6 over 5. So solving for p, divide both sides by 4. I get p is negative 3 over 10. So that means that my vertex is at 0, 0, okay, which I found. If I move up a value of p, I will then be at the focus. Okay, so vertex. Vertex is here. I know that's 0, 0. Okay, and it's y squared equals something, so I know it looks like this. So my vertex is at the origin. That means if I add p, okay, then um, I will have sorry, my focus, and if I subtract p or go in the other direction from the vertex, right? If I subtract by p, I will have my directrix. Okay, so I have the value in the middle. I know the value of p now. It's easy for me to find both of these things. Okay, so divide, I know what p is. Our equation then looks like this, right? Y squared equals 4px minus L plus p. So I put in my sort of standard form. So L plus p is 0. Okay, I know that p is negative 3 over 10. So then that means that L has to be positive 3 over 10. Okay, so my vertex is here. My focus is at negative 3 over 10. Okay. My directrix is at positive 3 over 10. Because remember, it's whatever this is. So my vertex is here. And then if I uh, add that to 0, I'm actually moving in the negative direction. Okay. And so that means that my focus is here and my directrix is on the other side. So my parabola, instead of opening this way to the right, it opens to the left. Okay, it'll open to the left because I have my vertex, and then lower than that is the focus, and on the other side of my vertex is the directrix. So it's the same parabola that I have, but flipped around. Okay, there you go. So the parabola opens to the left since the focus is to the left of the vertex, and the directrix will be to the right of the vertex. Okay, so let's go ahead and actually graph this real quick in Desmos. So here in Desmos, so let's go ahead and write our equation. So you have 6x plus 5y squared. What's going on here? 6x plus 5y squared equals 0. Okay, so there you go. My parabola opens this way. Okay, and so this is my vertex 0, 0. I knew that for p, it was negative 3 over 5. Okay, and so since it was negative, that means that I have to move into this direction. So my vertex, sorry, my focus is at 0, negative 3/5, 3/5, and my directrix is at x equals 3/5. Okay, oops, my brain is not mapping. There we go. Okay. So equidistant. So the distance from the vertex to the directrix is the same as the distance from the vertex to the focus, right? So if I know that the focus is on one side of the parabola, the directrix is on the other. And remember, the focus is always on the part where the concavity opens towards, and the directrix is always on the outside of the parabola. So the focus is inside and the directrix is outside and they're equidistant. So once I find P, I know how much I have to move in any, direction. And so that's how that problem works for us. Okay. So let's move on to the next example, which is we're going to talk about ellipse. Okay. So now for an ellipse, ellipse is a little bit different than the parabola because it has two foci. So if we go back to our general shape, just to remind us, we got less stuff to go over. Um, this is an ellipse, right? It's like an elongated circle. It's like squished on one side, stretched out on the other. Boom, boom, boom. Okay, so an ellipse has two foci, which we'll call F1 and F2. And if you take, again, any point that's on the ellipse, let's say P, X, Y, and then find the distance from that point to F1, and from that point, which we'll call P to F1, and the distance from that point to F2, which we call the distance from our generic point. to the second focus. Okay, the sum of those two distances will always be the same, right? So just like before, the distance from the directrix to the focus was always equal to each other, right? They were always the same. And so here, if I'm adding the distance from one focus to the point and from the point to the next focus, the sum of those two distances always adds up to the same value, okay? Which is coincidentally the same length as what we call the major axis, okay? So regardless of what point we choose, so any generic point, this is going to be true, right? So every ellipse has a major and a minor axis. The major axis runs long ways through the ellipse through the center, okay? The minor axis runs through the ellipse as well through the center, but it connects to the short ends of the ellipse. Okay? So like this. So on the long ends, we call these the vertices. So the vertices are the ends of the major axis, right? This is the minor axis. It goes through the center, but it's the short side. Okay, this is the long way side. If we have a tilted parabola like this is now the major axis, and this is the minor axis. And again, the vertices are at the end of the major axis. Okay, we have a rotation. It's the same thing. It's the long ways, right? So here the key is that all of the blue lines represent the major axis. All the red lines represent the minor axis. Okay. The length from the center of the ellipse to the end of the major, so half of these distance, so from the center to one end or from the center to the other end, okay? The vertices of the major axis is A. So the distance from the center to vertex is A, and the distance from the center here to this vertex is also what we call A. So the whole thing is A plus another A, so 2A. For the minor axis, we say that it's a length of B. So from the center to one end is B, from the center to the other end is B, so altogether the minor axis has a length of 2B. The foci are along the major axis. Okay, so we have a vertex, then we hit one of the foci, then the center, then one of the foci, and then we have the last vertex. Okay, so everything lies along the major axis. Um, so we have two foci, and they're on either side of the equal sign. So everything is symmetric for our ellipse. Right? And the distance of the foci from the center is C. So we say that we move out a distance of C to get to our focus. Right? So from the center to a distance of A is a vertex. From the center out a distance of C is a foci. And if I go in the opposite direction from the center, up or down in this case, a distance of B, I get to the top or the bottom of my ellipse. Okay, so drawing a graph, this is my ellipse. This is the major axis. So from the center here will be A0. Okay, in the opposite direction, if I'm centered, on X and Y axis, centered at the origin, this will be negative A0. Right? If I move up, this will be at B0 or 0B, I'm sorry, and this will be at 0, negative B. To find the foci, have one on one side of the origin or the center and one on the other side. So at this focus, this will be a distance of C, and there's no up and down because I'm on the axis. Okay, and in the other direction, equidistance, same distance, is negative C. Okay, I can connect this point here, and I have a nice little triangle that I get to work with. Okay, if I rotate this and I orientate it differently, notice how my A is no longer on the x-axis, but it's on the y-axis, right? So it's not A0 anymore, it's 0A, because the distance from the center to the vertex, right, whatever the long way is always the distance of A. So from here to here, it's at 0A for the y value, 0, negative A, and my C's are located along this axis as well. And then going in the short distance, I get B and negative B to get to the left and right ends. And then I can connect B to C to my focus with a dot. So as we were saying before, the distance from any point on uh, the ellipse to one focus, and from that point to the other focus, that whole distance is always 2a. And so it's nice when it's in the middle here at B because um, it's equidistant, right? This one is right in the middle. If I had a point right here, it would be shorter to this point here and longer here. So right in the middle where it's equal distance is nice because it allows me to draw a triangle that I know something about, right? Because the distance again from the focus to a point back to the next focus is always 2a. So if this distance here and this distance is here is the same because it's in the middle, well, that allows us to draw a triangle where I have a distance of B, a distance of C up to the focus, and I know that this is A, right? This hypotenuse, I know it has to be A because, again, the distance from focus to any point back to the other focus is always 2a. It's always the same distance as the major axis length. Okay. And so since this one is right in the middle, that means this length and this length is the same. So if this length plus this length is 2a and they're equal, well, that makes sense that this is a. Okay. Same here with the rotation. I go up b. Okay. I go over c to the focus. And again, this point and the line from here to here is the same. So this distance to this distance is 2a. That means this has to be a and this has to be a, right? Now, if this point was not in the middle, where it was equidistant, let's say I was looking at a point here, it would not work to say this would not be a and this would not be a. Very, very obviously not so. Okay. So when I'm looking at this right in the right place, I have a nice little reference triangle that I can use. So for instance, let's say I know where the focus is and I know the length of the major axis. Well, then I can find the length of B in that case. Okay. Or let's say that I know my length for A and my length for B. I could figure out where the focus is out of this right triangle. If I know, I don't know, let's say I know this length and I know this length, I could use those two values to figure out where C is, right? So again, because of Pythagorean theorem, in this case, C squared is always going to be A squared minus B squared. Okay, same thing here. So that's, if I have any two of these, A and B or A and C, B and C, whatever, I can always find the third out of this relationship. So the equation for an ellipse is going to vary, obviously, depending on which axis is the major axis, right? So the equation for this is not going to be the same as the equation for this, right? So um, my equation is going to tell me which orientation I have. So whichever value we have in the denominator, we're going to have fractions here. One value will be under x squared, another value will be under y squared, okay? And whichever one is larger will tell me which axis the major axis is on, okay? So my general formula is x squared over a squared plus y squared over b squared equals a. So here, um, a is always larger than b, okay? So if you see here, b is the short side, right? A is the long side to the end, right? Short side, long side. So my general equation here, x squared over a squared, that means that a is the larger number, right? Because again, through this graph, a is the one that's larger, right? It's on the long side. And so since that's true, that means that because it's not going to say a squared, it'll be a number, right? It'll be x squared over, I don't know, 100 plus y squared over 9. Well, the bigger number is going to tell me which axis is the long axis, right? So if the bigger number on the denominator is under x, then that means that along x is the long axis, okay? If the bigger number is under y, well, then it's telling me that the long axis is along the y-axis, right? So whatever the big number is, whatever number it's under, that's the one that's the long one, okay? And the shorter one tells me which one is the shorter one. So let's do an example. So let's consider the ellipse that's given by the equation 9x squared plus 25y squared equals 225. So again, this is not in standard form. If you just looked at this, you might think it was a circle because you can see x squared and y squared equals something else squared. Um, So why wouldn't this be a circle? Well, remember, an ellipse is a circle that's been elongated and shortened for the different axes. So in order to figure out what this is going to be in standard form, I'm going to divide both sides by 225. Okay, so that's going to give me x squared over 25, y squared over 9 equals 1. Now I'm in the standard form. Okay, the bigger number is under x. That means the long axis is x. And remember, we're using the square roots of these, right? So since this is 25, that means that my long axis from 0 to one end is a distance of 5. And on the short side, it's 3, right? Because I'm using the square roots of 25 and 9 to figure out what a and b are. Because I have a squared and b squared here. So this tells us that the major x-axis and a is the value of 5. Okay, so if I'm centered at this at the origin, I go plus or minus 5 and 0. These are going to be the vertices for the major axis. Okay, for the minor, it'll be 0 plus or minus 3. Okay, because b is 3. So from the center, I go up 3 and down 3, and those are going to be the vertices for the minor axis. I have this relationship, right? I know what A is, I know what B is, so I can use those values to find C. So a squared is 25, b squared is 9. So 25 minus 9 is c squared. So that means that c is 4. So that means that at plus or minus 4, that is where the foci are located. Okay. So if I look at this graph, it looks like this, right? So the long axis is along x. Okay. So I go from the center to 5 for one vertices, from 0 to 5 in the other direction. Okay, since it's on X. On the Y, I go up 3 and down 3 to find the vertices of the minor axes. And then in order to find C, I'm using that C squared equals A squared plus B squared. And so it's easy for me to find the two foci. Okay, pretty straightforward once you see how that works. So let's go now on to hyperbolas. Okay, so hyperbolas are a little bit different. There's a little bit more to them. They look harder, but they're actually not that bad to work with. A hyperbola also has two foci. So these two foci are centered along what we call the transverse axis in the direction of concavity, like in a parabola. So the transverse axis is what you can think of as a line that connects the two vertices. Okay, so the two vertices of a hyperbola are connected. So we come back just in case you're like, I don't remember what a hyperbola looks like. Boom, boom, boom. All right, we're moving along. There we go. So this is a hyperbola. So the line that connects these two vertices is called the transverse axis. Okay, connects these two. That's the axis in question. All right. Yeah, we did a lot. Okay, so a hyperbola has two foci. The center along the transverse axis in the direction of concavity, like in a parabola. So what do I mean by that? The transverse axis connects the foci, or I'm sorry, connects the foci, it connects the vertices as well. Okay, so it connects the two sort of tops or ends of the hyperbola, and then the two foci are inside of the curve of the hyperbola. So just like with a parabola, the focus was inside of the parabola and the directrix was outside. So for a hyperbola, you basically have two parabolas that are facing away from each other. Okay, although their shape is not parabolic. The curve that's there is not the same thing as a parabola curve. It changes differently. Okay, actually. And so the foci are on the insides of each respective parabola looking thing on the hyperbola. Okay, so basically what this is saying is that the foci are inside of the parabola. They're like covered by the parabola. Okay, they're not between them, they're on the outsides, on the insides. Any point on our hyperbola is going to have the same difference in distance to each foci. So if I take any point on my parabola, um, the distance from one parabola to the next. So very similar to what we did in ellipse, right? So focus to the point to the next focus, right? So I'm looking at the difference in values between the two distances. That's always going to be 2a, right? So in an ellipse, the sum of those was 2a. In a hyperbola, the difference, the distance between those two, the differences and the distances between those 2 points is always 2a. Okay. So the two pieces of the hyperbola are called the branches. So A is the distance of a vertex from the center. The transverse axis has a length of 2a. So the center of the parabola, you go from the center of I'm sorry, hyperbola, from the center of the hyperbola to one vertex is the distance of a. So that means that the two um, hyperbola branches have a distance of 2a away from each other. Okay. C is the distance from the center to the focus, not from the vertex to the focus, right? From the center. And we can find it with c squared equals a squared plus b squared. So instead of subtracting, we're using the sum of these in order to find that value of c. An invisible rectangle is called the central box, and the line that connects opposite corners of that central box is gives us our slant asymptotes for the hyperbola. Okay. The box is formed um, between the two branches of our hyperbola and has side lengths of 2a and 2b, right? And it'll be very clear to tell which one is 2a. So the distance 2a comes from the distance between the two vertices, okay? The distance of 2b is just the imaginary line, basically, okay? So a hyperbola has two slant asymptotes. Okay, y equals plus or minus b over ax, or y equals plus or minus a over bx, depending on the orientation. A hyperbola with transverse axis at the x-axis, okay, meaning that the center is it's along x, is going to have the equation x squared over a squared minus y squared over b squared equals 1. Again, here the a is going to be larger in value than the b, okay, and that's going to look like this. So we have our graph. This is our center. Okay, and the distance from the origin to one vertex is a, and so the distance from the center to the other vertex is negative a. So it's very clear that the distance between them is 2a. Okay, that line there is 2a. The foci are inside of the concavity, right? So C and negative C. So from the center to C is one, and from the center to negative C is the other. It's along, right? It's in the same directions along the transversal axis. Okay. B goes in the opposite direction, right? It goes up and down, and really just gives us the heights for the box, and A gives us the width of the box. Okay, so the box goes up B and down B, so it has a height of 2B and a width of A and negative A, so it's a width of 2A. And now the line that connects these two corners and these two corners of the box create the slant asymptote, which our hyperbola will get infinitely close to, but never touch, right? This one gets infinitely close to it, but never touches. And so it's negative b over a is this one, right? It's on the origin. And to get to a point here, I go over a, down b, right? So my up and down is b, and it's negative, and my over was a, so that should make sense. So then the line that connects this one, the slant asymptote, if I start at the center, I go up B and over A, right? So that'll be y equals B over A x. Right? Those are all of our points. So if I know A and B, I know this box, I know the slant asymptote, I know where the vertices are, and then I can figure out where the centers are because we have this relationship with A and B that c squared is a squared plus b squared. So our form of our equation looks very much so like the form of a ellipse, except an ellipse is plus, right? It's positive and positive. They're being added together. For a hyperbola, you're going to have a subtraction sign in it. Okay, so it looks exactly the same as an ellipse, function form-wise, okay? But it's It's different because there's a negative sign there. Things are being subtracted. Okay. So again, the blue is the transverse axis. So a hyperbola with transverse axis at the y-axis instead of the x-axis will have this as the equation. Okay. Again, a is the larger number here, right? Whichever square is largest on the bottom, whatever it's under will tell you the alignment. So if the larger number, okay, if the larger number is over x, well, that means that we are aligned along the x-axis. If the largest denominator is under y, then that tells us that we are aligned. Our transverse axis is up and down instead of left and right. Okay, so the transverse axis is up and down, meaning our hyperbolas open upwards and downwards instead of left to right, right on the x. So largest is along y, that means it's up and down. If the largest denominator is along x, then we're left to right. Okay, so here everything is the same. Instead of moving left to right, I'm moving up. So I move up a value of A to get to a vertex, down a value of A to get to the vertex, right? Up a value of C and down a value of C. I move to the right B and to the left B, and I can find my slant asymptotes and this central box boundaries just by A and B, right? Because all of that's given to me, right? So the central box, the slant asymptotes, and the vertices, those are all given just in the equation, right? And then in order to find C, I would use the A and B given in order to find that using that relationship that I have. Okay. Now, sometimes we're going to get asked questions like, here is your slant asymptotes, right? Find the equation of this hyperbola. So you're not given the equation, but you'll be given some information about the hyperbola or the parabola or the ellipse, and there'll be enough information to figure out A and B, and then you have to figure out the rest and uh, form your general equation from there. Okay. So let's do an example. So let's consider the graph provided. Okay, so here they're telling us what the vertices are, and they're giving us the slant asymptote. We have all the information we need to find the equation of the hyperbola. And if I want to find the foci, I can find the foci as well, right? So just from this orientation, I know that A is equal to 3, and it needs to be under the y term because it's up and down, okay? It should be very clear here that B is going to be 4, right? Because it was always A over B in this case, right? Because if this is 3, then that means its denominator has to be 4. And so that's enough for me to find my equation. That's it. That's all I needed. Okay. Now, if I want to find the foci, I can do that too, right? I add these together, right? So it's a squared plus b squared is c squared. So take those two values, add them together, take the square root. That's 25. So root of 25 is 5. So my foci are past my vertices, which they should be. So it's 0 and plus or minus 5. Okay. And that's all the information. I found everything just from those pieces that I had. Okay. So now let's talk about the last part of this section, which is shifting conics. Okay, so we can shift conics just like we can shift a function. I go into, again, great deal of this in my pre-calculus, I think chapter 2 or something like that. But we also do this in the Calculus 1 material for the review. So if you're fuzzy on this, you can look at functions and how to shift functions. Just as a review. It's very similar to that. So basically, we'll be shifting things by X and Y. We're not going to be doing any rotations. In my pre-calculus course, we do go over rotations of an ellipse, um, but I'm not going to revisit that until linear algebra, basically. Um, but yeah, we're going to shift this just like we would shift a function, right? By adding stuff to X or adding stuff to Y, right? So let's go ahead and do an example. So from this example, I know that this is an ellipse, right? Because I have an addition here. If this was a subtraction, I would say it was a hyperbola. I know that the biggest value is under y. So this is an ellipse whose major axis, long ways, goes up and down, right? It aligns with the y-axis. I know the center of my ellipse is shifted down 2 units, right? Because this says y plus, so we always go in the opposite direction. and it is shifted to the right in the positive direction 3 units. So my whole ellipse goes up and down, but it's been shifted down and to the right. Okay. The small side has a length of 4 from the center to either end, so a total length of 8. Here, it's a length from the center to either vertices is the length of 6, so that's a total of 12 from top and bottom for the major axis, and a total of um, again 8 for the minor axis. I think that's pretty much it, right? If I need to find the foci, I can find the foci using that formula that I have. Now I have to remember that I'm finding the distances here. I'm not finding the actual equation. So anything that I find for the foci, the vertices, I have to shift by how much my entire ellipse has shifted. Okay. So this is an ellipse that's been shifted right 3 units, okay, down 2 units as I stated, okay. So that means my center is at 3, -2. So that means the major and the minor axis both have to go through this point. So looking at A and B, I can find out the lengths of those, but I got to apply that through this point, okay. So my minor axis is located at y equals -2, okay, running parallel to the x-axis, the small side, and with the length of 8. Okay, as we said before, because it's 4 and there's 2 of them. The major axis is at x equals 3, okay, and it's running parallel to the x-axis, right, up and down, right, because it's the long side, and it has a length of 12, right, 6 up and 6 down, so a length of 12. So the minor axes vertices are then going to be located at the center, which is 3, -2, but I know that this length is 4. 4 in one direction, 4 in the other direction. So I take 3 and I add 4 to it, and I can take 3 and I could subtract 4 from it to find one vertice and the other vertice on the minor axis. Okay, so that's -1, -2, and 7, -2. So from 3, -2, that's 4 in one direction, 4 in the other direction. That's a total length of 8, and it's centered at the y value of -2 because that is how the minor axis runs. The major axis runs top to bottom, long ways, along y, parallel with y. And so I'm going to take my point 3, -2, and I know it's a total length of 12, so that means it's 6 in one direction and or 6 up and then 6 down to get the vertices to the end. So I'm going to start at the center, 3, -2. I'll add 6 to it, and I'll subtract 6 to it. So -2 plus 6 is 4. -2 minus 6 is a -8, right? Same thing here. 3 plus 4 was 7, and 3 minus 4 was the -1. So that's how I found these 2 points. Okay, so now I have the endpoints for the short axis, the minor axis. I got the endpoints, the vertices for the major axis. And so the only thing that I really need now is to find the foci. And so I use my c squared equals a squared plus b squared, okay, or minus b squared. So the foci is at 36 minus 16 square rooted, which is 2 root 5. And so I know that it would have been here on the y-axis, right, or on the x-axis up and down, but I've been shifted. So I'm at 3, -2, and I have to move up or down because remember, the foci are on the major axis. And so my major axis is it runs along x equals 3. Okay. So it would have been at 0 plus or minus 2 root 5, but since I'm starting from 3, -2, and I need to move up or down, that means I move on the bottom. So it's going to be at 3, 2 root 5, or I should just say -2 plus or minus 2 root 5. Okay. So 3, -2 is where I started at. I will add to that 2 root 5, and I'll subtract from that 2 root 5 in order to find the 2 foci. So looking at everything, I'm at 3 minus 2 is where my new center is. Okay. The top part is at 3, 4. Okay. 3, 4 is top of the major axis. 3, -8 for the minor axis, for the bottom of the major axis. I am at 7, -2 for the end of the minor, and at -1, -2 for the other. Okay, and then the foci are I'm at 3, and then I start at -2, and so from here I move up 2√5 to find 1, and from the center I move down 2√5. So I had to apply the shift to all of the points. Okay. So that's how we shift the conic. Hope that was helpful to you. Again, the pre-calculus course goes into depth into parabolas with more examples, into depth for ellipses with more examples, and into depth with hyperbolas with more examples, and into depth into the shifted conics as well. Okay. Hope this was helpful. If you're already kind of familiar, hopefully this was enough to um, get you a basic understanding of the conics. So in the next section, the last section, we're going to talk about the polar forms of our conic equations, okay, of our conic sections.